Good afternoon. My name is Islam Harun Rashid. Today I'm going to presentation on my given paper, which is DNS cache poisoning attack recorrection with side channel. The main objectives of the topic. The first, I'll overview of the given paper, and then I'll discuss the topics step by steps. So I'll discuss DNS introduction, and then I'll discuss what is DNS cache poisoning, then traditional DNS cache poisoning attacks, then side channel and DNS cache poisoning. In addition, recorrections with side channels. Furthermore, side channels attack, ICMP message and impact on UDP, ICMP based ephemeral port scans, then mitigations and preventions, and then conclusions. So the overview of research paper which is given to me is DNS cache poisoning. So DNS cache poisoning is a type of cyber attack that involves corrupting or poisoning the DNS, domain name system cache of a target server or resolver with malicious data. This malicious data can lead to the redirection of legitimate domain name requests to malicious websites, intercepting sensitive information, and enabling various other type of cyber attacks. DNS cache poisoning attacks can have serious consequences, including data theft, phishing, and spreading malware. Resurrections with side channel refers to a more sophisticated variant of DNS cache poisoning attacks. In this context, resurrections imply that an attacker attempts to revive or repress malicious DNS cache entries to prolong their impact, and side channels refer to covert channels through which information can be leaked or manipulated. The key components of a DNS cache poisoning attack involving resurrections and side channels may include introduction to DNS. The DNS domain name system is a hierarchical and distributed naming system used on the internet and in private networks. It is designed to translate human-friendly domain names into the numerical IP addresses that computers use to identify each other on the network. Instance, DNS serves as a crucial address book for the internet. DNS servers are specialized servers that store and manage database of domain names and their corresponding IP addresses. They act as intermediaries facilitating the translation of domain names to IP addresses and vice versa. DNS provide human readable domain names, making it easier for user to access websites and services. Remembering IP addresses for every website would be impractical. seamless internet navigation. DNS ensure that users can easily switch between websites and services without needing to know the underlying technical details of network addressing. Load balancing. DNS can distribute incoming network requests across multiple servers, improving efficiency and redundancy for websites and online services. DNS can be configured to provide failure and backup capabilities, ensuring that services remain accessible even during network outage or server failures. DNS is distributed globally, making it possible for users worldwide to access the same website using the same domain names. Efficient network management. Network administrators can use DNS to efficiently manage and organize their network resources, such as configuring email servers or setting up subdomains. DNS hierarchy. DNS hierarchy is the steps resolver DNS hierarchy and attack style. In figure 1 shows a DNS hierarchy, DNS hierarchy. The step resolver runs on an individual client and act as a proxy. It only forwards the query to the upstream DNS server without resolving the query itself. The sole purpose of the step resolver is to provide the local cache to speed up DNS queries from the same host. In the next layer of DNS forwarders are also caching proxies, common in home and business gateways such as Wi-Fi router, but they serve multiple clients in a WAN. At the highest layer, DNS resolver finally performs the real name resolution task by recursively consulting the same name servers where the actual DNS records are stored. How DNS works? User user initiates a DNS query. When a user enters a domain name, like in a web browser, their device needs to know the corresponding IP address to establish the connection. Local DNS resolver, DNS client. The user's device, often provided by the internet service provider, ISP, or configured manually, sends a DNS query to a local DNS resolver, and that is also known as DNS resolver or DNS client. Local DNS resolver cache. The local DNS resolver checks its cache to see if it already has the IP address for the requested domain. If it's present, it can respond immediately without further queries. Root DNS server. If the IP address is not in the cache, the local DNS resolver contacts a root DNS server, which is the starting point of the DNS hierarchy. Top level domain, TLD server. The root DNS server in turn refer the local DNS resolver to the appropriate top level domain. DNS server based on the domain existing, like .com, .org or .net. This basically function has also now been used by various security services such as email authentication, routing security, and even certificate issuance, where proof of domain ownership is the common method to acquire certifications. As a result, compromising DNS can lead to catastrophic security failure with a wide range of sequences. Cache poisoning. Cache poisoning in the context of the domain name system, DNS, is a type of cyber attack aimed at corrupting the data stored in DNS caches. This attack can lead to malicious or incorrect IP addresses mapping for domain names, potentially redirecting users to fraudulent websites or intercepting their communications. DNS cache poisoning attacks. DNS cache poisoning attack was first popularized by Dan Kaminsky in 2008 after the ephemeral port number was randomized. Fragmentation attacks were invented to eliminate the need for guesses and sources for sorry, I'm suffering fever with cold. So fragmentation attacks were invented to eliminate the need for guessing the source port by replacing the second fragment of the original DNS response. These attacks usually have some strong assumptions like predicting the IP ID of the packet or running puppet on the victim resolver. For extension attacks, they randomize the ephemeral port number by adjusting all for one available ephemeral port. In 2020, ZDNS was invented as the first side channel based DNS cache poisoning attack. However, this attack is slow and usually takes tens of minutes to finish. Present a novel way to poison DNS caches by exploiting domain parsing ambiguities. The attacks could be happen based on another unique side channel in ICMP and provide another way to poison the DNS cache using the first ICMP based port scan. How does cache poisoning typically works? Initial query. An attacker sends a DNS query for a specific domain to a domain resolver server. Quick response. Simultaneously, the attacker sends a false DNS response to the DNS resolver, claiming to be authoritative for the requested domain. The port's response contains malicious IP address information. Cache update. If the DNS resolve accepts the port's response and caches it, future DNS queries for the same domain will be answered with the malicious IP addresses. Redirection or data interception. When users request the affected domain, they are redirecting to a server controlled by the attacker. This server may host a fraudulent website or intercept traffic for malicious purposes, such as phishing or data theft. Side channel. What is side channel? Side channel attacks typically aim to extract sensitive information such as encryption keys or data. By observing and analyzing various unintended physical or operational characteristics of a device or system, side channel attacks are particularly concerning because they can bypass traditional security measures. that focused on protecting data in transit or rest. Such channels have been reversed in network attacks, especially reverses IP-ID global counter to probe often ports that utilize that utilize the stateful firewall to infer the TCP sequence number. Uses global challenges SCK counter to infer the TCP sequence number and hijack the TCP connection of path. Besides, nowadays presents an automated tool for finding side channels in the TCP stack using model tracking and found several other side channels inside the Linux TCP stack. Cache attack is one of the most concerning side channel attacks. These attacks focus on exploiting variations in memory access patterns, particularly in CPU caches, to gain information about data access patterns by keys. Resurrections with side channels. Resurrection typically refer to the recovery or reactivations of cryptographic keys or data that was previously considered inaccessible or securely stored. Resurrections with side channels is a term in the field of computer security and cryptography that refers to the use of unintended information leaks, known as side channels, to revive or recover cryptographic keys or sensitive data that were thought to be securely protected. This concept highlights the importance of defending against side channel attacks and strengthening the security of cryptographic systems to prevent the potential resurrections or recovery of sensitive information by malicious actors. ICMP message and impact on UDP. ICMP is a diagnostic protocol used to signal errors during the delivery of IP packets. When a router discards the packet and returns an ICMP TTL expired message back to the source after it detects that the TTL of the forwarded packets reaches 0. To allow the source to destination which packet have encountered errors, a partial copy of the packet is embedded in the ICMP message, which includes the source and destination address, source and destination port. The source should accept such messages only if the wrapped 4-tuple message an existing socket. Upon validating the correctness of such an ICMP message, ICMP based ephemeral port scans. Prior methods of UDP based port scans. Traditionally, UDP probes are used to determine whether a UDP port specified as the destination port number in the probe is open or closed. According to the RFCS, if the destination replies with an ICMP port unreachable message, it indicates that the port is closed. This is traditionally used to probe server ports as shown in figure 2a. In addition, this can also be used to discover public-facing ephemeral ports. It is obviously that the presence or absence of the ICMP response is explicit feedback on the UDP port. So this is UDP based port scan patterns. Here UDP port is working, 53 is working, but UDP port 67 or ICMP 67 is not working. On the other hand, ICMP based port scan, here ICMP UDP port 53 is working, but ICMP UDP 67 doesn't work. DNS. The DNS to scan private passing ephemeral ports. UDP probes must be sent using the source IP address of the remote pair, forcing an off-path attacker to find an indirect way of performing the scan, enabling an attacker to send spoofed UDP probes and indirectly infer whether they have solicited responses, especially if a guessed port number in a spoofed UDP probe happens to match the correct ephemeral port. The resolver will not generate an ICMP message. Otherwise, it would be. This results in either a stationary limit counter or a decrement of the counter. An attacker can then check whether the counter has been drained by attempting to solicit ICMP response with a UDP probe from his real non-spoofed IP. ICMP based port scans. An ICMP message embeds the header of the original packet from the source, including the source and destination port information. This opens up an opportunity to craft an ICMP message embedding a guest port number, which is used to match a specific socket on the receiver end. However, the challenges is that ICMP messages are by design error messages, usually for diagnostic purpose only, which do not solicit explicit response. This means that regardless of whether a port number is guessed correctly, the receiver will not provide any response as shown in figure 2, making the ICMP based port number infeasible. This is port number inference. So number A is the fragmented based public port inference. Number B is redirect based public port inference, and the C is fragmented based private port inference. I will discuss this in later. And this is the victim port number, and this is the off-path attacker. So public facing port number interference. The basic idea of public facing imperial port scan is in figure 3a and 3b. Public facing imperial port is introduced as called wildcard socket in the kernel terminology according to DNS software. It turns out that Linux or other OSs treat such public facing port much more generously and accept any inner destination IP addresses in an ICMP message, as long as the inner source addresses matches the resolver's IP and inner source port matches the ephemeral port. This effectiveness that against such public passing port, one can easily trick the resolver to update the MTUs for any remote IPs. Public facing port number inference. To observe the change in the cache, the attacker can simplify send a ping or any other packet from the resolver, the observe if the response will be fragmented as a result of the lowered MTU as shown in figure 3b. If ICMP redirect is used for probing, the effect is that the victim resolver becomes unresponsive because the traffic to the attacker will now be redirected to a wrong gateway IP set in the redirect message. Private passing port number interfaces. Most DNS software like BIND will produce private passing imperial port rendering the previous method invalid. The first adjustment we have to make is to set the inner destination IP address to the IP of the name server. This because UDP4 library lookup will check the complete 4 tuple of the embedded UDP packet to locate the socket that has previously been connected to a specific remote IP and port. Conditions of successful attacks. The key necessary conditions for a resolver to be considered exploitable. C1 must check the port number in the embedded UDP packet for an ICMP error before processing. C2 must catch the MTU or next hop information. C3 must not ignoring the ICMP fragment needed or ICMP redirect message in the kernel. And C4 must not shut down or retransmit the query after receiving ICMP message. Mitigation and prevention. We conduct our experiments with ethics as a top concern during the measurement of the vulnerability populations in the wild. To mitigate the attack, we suggest setting proper socket options, randomization the caching structure, and rejecting specific ICMP messages when possible. We summarize our contributions as follows. We discussed novel side channels that allows us to use ICMP probes to scan UDP ephemeral force. We thoroughly analyzed the root cause of the discovered side channel and developed powerful DNS cache poisoning attacks based on that. We measured their impact in the real world and proposed corresponding mitigations, querying our own domain at meet speed for each resolver under 1000 packets per second. So we avoiding some suspicious looking packets. Conclusions. This paper represents novel side channels during the process of handling ICMP errors, a physical overlook attack surface. We find that side channels can be exploited to perform high-speed off-path UDP ephemeral port scans. By leveraging this, the attacker could effectively poison the cache of a DNS server in minutes. So we show that side channels effect may often resolver and thus have serious impact. Finally, we represent mitigations against the discovered side channels. Thank you so much for your time.